Hello friends, good afternoon and welcome to EduSat live lectures. Dear friends, today we are going to talk about residual entropy, spontaneity and equilibrium. To discuss this topic, we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome sir.
Thank you very much. First of all, again, I wish very good afternoon to all the viewers of the series on chemical thermodynamics. So, as you have already seen, we have progressed with a number of lectures in the series called chemical thermodynamics, and we have reached to a state we have discussed a lot about entropy changes also, how the entropy changes in natural transformations, and this has led to important conclusion called Clausius inequality, following which we did also try to see what way the entropy changes in all natural processes is the answer to the question what actually is the entropy. So, if you remember back while I introduced the concept matter subject or concept of entropy, I said that it is a better question to ask how the entropy changes in a natural transformation and how it can predict the spontaneity of a process, rather than asking such questions actually what entropy is. So, with that, today the topic is again main topic is spontaneity and equilibrium, but we would like to start with from where we had actually left in our previous lecture. We were on the discussion of statistical interpretation of entropy, and we did try to understand what actually the statistical interpretation of entropy means to us, and we learnt that as the energy of the system, internal energy of the system increases and the volume of the system increases, then in that situation the spatial distribution of the number of increases, it means the number of ways the system can be arranged in a greater space is much more as compared to in a smaller space. So, therefore, as the volume increases, the number of arrangements in which the state of the system can be achieved increases, and that will lead to an increase in the entropy of the system. And similar is the situation when internal energy of the system increases, it leads to a broader energy distribution of all the constituent particles over a range of energies, and that will lead to again increase in entropy of the system. That is what actually we learnt in our previous lecture. And I said that third law of thermodynamics, as it says, the entropy of a pure perfectly crystalline system is 0 at absolute 0 of temperature, but there are certain exceptions to this law. There are certain chemical species which do possess entropy even at absolute 0 of temperature, and such in that entropy being possessed by such crystalline substances, perfectly crystalline substances too, is called residual entropy. And today we need to learn what way the residual entropy, what is the reason and what statistical interpretation actually what we have made till the time has an answer to what is the reason why this residual entropy actually exists for even perfectly pure crystalline systems. So, this is all we need to first of all see this, and thereafter we will switch over our attention to spontaneity and equilibrium, which again emerges from the discussion of topic matter of entropy. So, here we start with, you see, before we go any further, we would like to say that in a natural change both system and the surroundings are involved, and if you remember back the Clausius inequality, we discussed that it is the total entropy change of a system which is isolated in nature do increases in a natural transformation or in a spontaneous transformation. And since we said that this isolated system can be considered as being made up of a system of interest and its immediate surroundings. So, for any particular system, its entropy of change in the system along with that of the surrounding should actually increase in a natural process or a natural change. For example, universe whose entropy always increases. So, universe must reach a state of higher probability and therefore higher entropy. Now, having said this, coming over to the discussion, as I talked about the residual entropy, now consider a situation. We have suppose a metal rod, for example. What is actually a metal rod? It is a piece of metal, some piece of metal. Let us consider. In a piece of metal, there are a large number of constituent particles. Which are the constituent particles? The atoms. If we have a crystalline solid which is made up of molecules, then the constituent particles will be the molecules, not the atoms. But in the case of metal, a piece of metal for example, the constituent particles will be the metal ions. And a C electron model suggests that a pool of, it is like a pool of mobile electrons which surrounds all these metal ions, and metal ions are present at fixed lattice sites. So it means each metal atom is present at a crystallite site in the lattice of the host material. For example, we talk about iron piece of iron metal or aluminum metal or so on. So what it does mean that the constituent particles are present at fixed lattice sites. Now having said this, in a pure crystal, atoms are located in an exact pattern of lattice site. There is also a pattern of lattice sites, shape, all the crystals has a particular shape, and a pattern of lattice means arrangement of these lattice sites. So it does mean that in a metal piece, in a piece of metal, there will be large number of sites in which the metal atoms which are being occupied by these metal atoms. So it is just like n, again can make an analogous situation, that n balls to be placed on n sites. It is just like that, n atoms to be placed on n available vacant sites. So now the question emerges, how many ways these number of atoms, or you can say the number of balls, for example, again we go back to this statistical interpretation, how many ways are there in which the number of atoms can be arranged on these fixed same number of lattice sites. It is very important to note over here is that the number of sites are equal to the number of atoms which are here the constituent particles in a piece of metal, right. Suppose there are n, it does mean the number of vacant sites which are available in which the atom needs to be occupied, they are same as the number of atoms obviously which they fill it. So now the question arises, if we choose the first atom, if we place the first atom on the first site, how many ways are there of choosing this atom? Since there are n atoms, so there are n number of ways of choosing the first atom. Then suppose once we choose the first atom, place it there, then we need to choose the second atom to be placed at second lattice site. Then how many atoms we are left with? We are left with one less. So it means if initially there were n atoms, so now we are left with n minus 1 atoms. So how many ways are there to choose the second atom? N minus 1 number of ways. Choices we have, I am talking about choices. We have initially for the first atom we had n choices, and for the second atom we have n minus 1 choices out of the remaining n minus 1 atoms. Similarly, for the third site to be placed with an atom, we have n minus 2 choices. For fourth site we have n minus 3 choices, and if we keep on looking like this, ultimately for placement of last atom we will be left with only one choice. So how many choices in total we will have for placement of these n atoms on n lattice sites? The choices will be the multiplication of all these individual choices. It means we need to multiply n into n minus 1 into n minus 2 into n minus 3 into n minus 4 and so on and so forth, ultimately up to 1. What this is equal to? This is equal to n factorial. So what it does mean? It does mean that there are n factorial number of ways of choosing the n number of balls on n particular vacant sites. Having said this, now question arises, if we place, suppose on the first site a particular number of ball or atom, for example, does it make any, is it any different from if we place second atom or third atom, since all atoms are same? So, all these arrangements are indistinguishable. So, it means though we are talking about the number of choices which we are available with to choose the atoms on a particular n same number of sites, then if we need to talk about distinguished arrangement, we need to divide this n factorial number of choices by same n factorial, because n is the also the, since n are the number of atoms which are available. So, there are n factorial number of choices for this choosing these n balls on n sites, but all such arrangements are indistinguishable. So, if they are indistinguishable, so we need to again divide this whole number by n factorial, because there are n atoms. So, therefore, if we talk about distinguished arrangements in which this state can be achieved, state means arrangement of n atoms on n lattice sites, that will be the complexion of the system given by symbol omega, which is equal to n factorial by n factorial. So, now it does mean that complexion for such an exercise, for such an system in which we need to place n number of atoms on n same number of lattice sites is equal to 1 unity. So, we would see here the omega will be equal to 1 over here, because n factorial choices needs to be divided by n factorial indistinguishable arrangements. So, therefore, this becomes the distinguished arrangements, that is omega, which is equal to 1. So, for this situation means for this crystalline state of a piece of metal, therefore, at absolute 0 of temperature we have its entropy given by Boltzmann relation, that is as equal to k ln omega, and omega is 1 here. And you must know that logarithmic function which operates on unity, it results to 0. So, it means s equal to 0. So, this relationship is in consistency with third law of thermodynamics, which says that entropy of a pure perfectly crystalline system is 0, and that is what the statistical interpretation has in store for us, and that is how statistical interpretation of entropy actually predicts for us that entropy for a pure perfectly crystalline substance is 0 at absolute 0 of temperature. I hope this point is well considered by you. Now, having said this, now suppose a situation, if now consider a mixed crystal. What we mean by mixed crystal? Now we say it means we may consider an alloy which is made up of which is basically a mixture of two particular kind of atoms. So, it means mixed crystal. If we consider a mixed crystal in which there are n vacant sites, and since the crystal is in mixed state, it means it has two different kind of atoms, A kind atoms and B kind atoms. Then it means this total number of n sites, we will have some number of A kind atoms and some number of B kind atoms, and the sum of these A and B kind atoms should be exactly equal to the exact number of lattice sites which are available. So, it does mean that n, which is the total number of atoms, is equal to Na, the number of atoms of A type, and number of atoms of B type. So, now question arises, in a mixed crystal what will be the entropy of such system? If we need to answer this question, we must know first of all what is the complexion of the system. So, again, since we have n number of atoms to be placed on n sites, so number of choices again will be n for the first site, n minus 1 for the second site, and so on and so forth, up to just one choice we will remain with for placement of last atom. But again, in order to look for the indistinguishability of such choices, we need to divide n factorial these number of choices by the n a factorial, which is the number of atoms of A kind, that is the, because such arrangements will be indistinguishable, and n b factorial also, because B kind atoms will also make indistinguishable arrangements, because you cannot distinguish between one atom or the other if it is of same element. So, that is why the total number of the number of complexion, then in that situation omega will be equal to n factorial by divided by n a factorial into n b factorial. Now, having said this, it is for sure whatever will be total n will be greater than n a and will be greater than Nb individually. So, therefore, it does straight away means that omega will be a finite value greater than 0, greater than 1, sorry, greater than 1. For a pure crystalline system, you must remember, just 2 slides back, just a couple of minutes back, we discussed that for a pure crystalline system, therefore, number of complexions were just unity, but over here the number of crystalline systems would be much greater than unity. It is very clear from this formula. Having said this, now let us talk about entropy of this mixed state S, which can again be calculated using S equal to k ln omega formula, that is Boltzmann relation. So, S equal to k ln omega, and omega is n factorial by n a factorial into n b factorial. Having said this, to evaluate this we need to apply an approximation. What is that approximation? It is a mathematical relationship, it is called Stirling relationship, because here we have a logarithmic term of ln, logarithmic term of n factorial, n a factorial and n b factorial. We need to know how to evaluate the logarithmic of a factorial number. So, in order to do that, we have an approximation in mathematics called Stirling approximation, according to which if we want to evaluate natural logarithmic rhythm of n factorial, then this is equal to n ln n, ln is natural logarithm, n times natural logarithm of n minus n. This is a simple relationship which is called Stirling approximation, which we can apply and we can evaluate the entropy of mixed state, that is given by S equal to k ln n factorial by n a factorial into n b factorial. Now, having said this, so if we apply this Stirling approximation, you see, if we say what is log of n factorial by n a factorial into n b factorial, this is equal to log of n factorial minus log of n a factorial minus log of n b factorial, and therefore, k log of n factorial according to Stirling approximation become n ln n minus n minus natural logarithm of n a factorial becomes n a ln n a minus n a minus natural logarithm of ln n b factorial become n b ln n b minus n b according to Stirling approximation. So, this is how this equation is generated to evaluate the entropy of mixed state. Having said this, now let us take these brackets away from here. When we take these brackets away, then minus ln, this is plus n a ln n a becomes minus n a ln n a here in this second equation, and minus n a becomes plus n a because minus sign is outside. Same is the situation over here, minus n b, minus sign was there outside the bracket, and within bracket n b ln n b minus n b was there. So, we have reversed the sign and we have written minus n b ln n b plus minus into minus become plus n b. So, now consider the situation, n ln n, this same term is written over same here, n is repeated here, n a minus n a ln n a again written here. Now, here plus n a plus n b, you can collect it to the right extreme side, and minus n a ln n a and minus n b ln n b, you can write it here itself. Now, having said this, this n a number of atoms of A kind and n b number of atoms of B kind, their sum is equal to total number of atoms n. So, that is exactly what happens in the next step. So, in the next step, S equal to k n ln n minus n a ln n a minus n b ln n b, up to this point this equation and this equation is same, plus instead of n a plus n b we can write n, capital N, the number of total number of atoms. Now, you can see total number of atoms n has also figures in here also and here also, but both times it figures with different sign, one is minus sign, one is plus sign. So, this cancels. So, then we carry forward to next equation, that is S equal to k n ln n minus n a ln n a minus n b ln n b. Having said this, now we can take a minus sign common from this equation, and what we get is S equal to minus k, and this plus term was there n ln n become here minus term, and these n a ln n a and n b ln n b were having minus sign. So, in this equation has they got plus sign, and then we carry forward this equation here. Now, here we need to do some incorporation of terms. You see, we are end up with S equal to minus K Na ln Na plus Nb ln Nb minus N ln N. We carry forward this same equation here. So, but what we have done is after K within these brackets, these square brackets, you can see Na ln Na plus Nb ln Nb minus N ln N. This is the same as in this equation. After that, what we have done, this is important to note, we have added Na ln N and we have subtracted also Na ln N. These two things figure in this bracket, since both these Na L natural logarithm of n minus Na L natural logarithm of n, both these are same in magnitude but equal but different in sign. So, therefore, they can cancel, they become 0, and here also we have also introduced Nb ln N minus Nb ln N. So, it means this bracket term also is equal to 0. So, it means this equation is this second equation is just the same as the first equation, only thing is we have introduced some terms Na ln N minus Na ln N, Nb ln N minus Nb ln N. This is a little algebraic transformation basically. Only thing is how we manipulate with the logarithmic term, that we need to keep track of. Then the algebra become very simple, easy, 4th, 5th standard algebra. Anyway, so S equal to minus K again. Now this whole bracket term will coin it as it is here, as it is. Now here what modification we do, just try and have a look. The Nb ln Nb, which has plus sign, we have taken from this bracket to this bracket, and minus Na ln N, which was having minus sign, we have taken to this bracket and we have taken a minus sign common. So, Na ln N minus plus Nb ln N minus taken as common, and then in bracket Na ln N plus Nb ln N. So, again these two bracket terms, you can see this bracket term and this bracket term, both are same in magnitude but has opposite sign. So, again is 0. So, again this equation is also same as that of this first equation. Having said this, let us carry forward this equation again. Now, you see what we try to do, since ln N Na plus Nb and minus ln N Na plus Nb, both these terms are same, both these terms are same. What we have done, just have a look, we have taken ln N common from this bracket term. What we will end up with, we will get ln N outside and within bracket we will get Na plus Nb, that is what we get. Ln N we have taken as common and Na plus Nb we get inside the bracket. Same thing we do with the term on below term, second term also, minus ln N Na plus Nb. So, again both these terms are same in magnitude but has opposite sign, so again is 0. Now, having said this, let us now talk about what is this Na plus Nb. What is this Na plus Nb? This is equal to capital N, that is total number of atoms. Number of atoms of A kind plus number of atoms of B kind actually equal to total number of atoms, that is N. So, what we can get is, instead of writing ln N into Na plus Nb, we can write here ln N, Na plus Nb become N, and we can write minus N ln N. So, for this term we can write Na plus Nb equal to N, and it become minus N ln N, this term, and plus N ln N from here also. Now, having said this, this plus ln N term is extra. This is a little discrepancy over here in this slide. This N plus N ln N term is extra. So, please make a note of this, that this term which I am pointing out over here, this is an extra. Having said this, now the question arises, what all this has to do with this mathematics. So, basically we can take all these bracket terms outside also. So, it is Na ln Na same term plus Nb ln Nb same term minus N ln N same term. Now, this Na plus Nb, this becomes as such, Na plus Nb becomes N. So, N ln N this term, and then minus Na This term we can now expand Na ln n with minus sign here and Nb ln n with minus sign here. So, this term with this explanation it is so let it be made clear once again, it is not extra. So, that was a mistake, by mistake I thought it to be extra, but it is not, sorry. Anyway, having said this, now what we can do is we can incorporate this in this equation. How? Na ln Na, same term we have written, Nb ln Nb, same term we have written. Now, next thing, minus Na ln n, this term we have written here, minus Nb ln n, this term we have written here. So, basically what we end up with here, what actually it all this means is that now we have a term where both NAs are common. So, we can take Na common in this first term and third term and Nb common in the second term and fourth term. What we will get? Na ln Na minus Na ln n, we can take Na common. So, as I said, so Na ln Na minus ln n, then plus Nb we can take common, then ln Nb minus ln n, and then Na ln. Now, what we need to do? What is this? Log A minus log B equal to log A by B. So, ln Na minus ln n equal to ln Na by n. So, what we get is this equation, minus k Na ln Na by n plus Nb ln Nb by n. Now, this number of atoms of A kind divided by total number of atom, would not that represent the amount fraction? The fractions of number of fraction of atoms of A kind, that is Xa, we can represent it with Xa. Na by n, that becomes Xa, and Nb by n become Xb. So, we get entropy relation this. So, then thereafter as equal to minus, now we can do multiply as well as divide this equation with n. So, when we multiply it becomes minus Na into k, and when we divide by n, so it becomes within bracket terms, it is like we are dividing each term by n. So, it is like 1 by n Na ln Xa plus 1 by n Nb ln Xb. So, it is like S mix, this is the entropy of therefore of mixed state equal to minus n k. Now, Na divided by n again become Xa, so Xa ln Xa plus Xb ln Xb. So, this is how we would say that S mix is the entropy of the mixed state. Mixed state means a crystal which is made up of two different kind of atoms. So, for that mixed state we have S mix, entropy of mixed state, which is equal to minus k Xa ln Xa plus Xb ln Xb. Now, question arises that if we imagine mixed crystal, now I said that there are, if this is a mixed crystal, then it has entropy associated with it. This formula clearly suggests. This formula, in this formula, why it clearly suggests, you can easily see Xa would always be less than 1, amount fraction, this is amount fraction. So, amount fraction, if there are two kind of atoms, so amount fraction of one kind of atom will always be less than unity. So, it does mean that we all know that logarithm of unity is 0 and logarithm of any quantity, any numeric quantity which is less than 1 is a negative value. So, it means Xa ln Xa will result in negative value and Xb and Xb ln Xb would also result in a negative value. So, in this bracket term would therefore be a negative value. When this multiplies with again negative sign and then total number of n is a positive quantity k, the Boltzmann constant a positive quantity, it means there will be a finite entropy associated with a mixed crystal. Now, imagine that mixed crystal, how it forms? Consider a reaction. Suppose the mixed crystal is being formed from pure crystal of A and pure crystal of B. Then it is something like we have taken two metals, fused them together, melted them at elevated temperature at beyond their melting point, and we have crystallized, allow them to crystallize and crystallize together. So, they form mixed crystal kind of alloy. And so, it means such a reaction, such a process would require some, would there be some entropy change in this process? That we would call as entropy of mixing, delta S mix, which is equal to entropy of mixed state, which is the final state, minus entropy of initial state, that is pure A, and minus pure B. So, we all know entropy of a pure crystalline substance, we have just observed that entropy of pure crystalline substance is 0 at absolute 0. That is also in consistence with statistical interpretation. So, it does mean in this relation, in this relationship S A and S B will be equal to 0, and therefore, delta S mix equal to S mix. It does mean that entropy increase for achieving a mixed crystal state is basically the entropy associated with the mixed state, and that can be quantified, that can be calculated using this derived relation which we have just derived here, minus n k x a ln x a plus x b ln x b. Now, we need to make some interpretation of this relationship, what this has in store for us. Since in an impure crystal has any impure crystal has at least the entropy of mixing, from this we can conclude at absolute 0, its entropy therefore cannot be 0. Thus, an impure substance does not follow third law of thermodynamics. This is first interpretation we can make from this relationship, entropy of mixed state, that is the requirement, that gives one requirement, that entropy of a crystalline substance will be 0 at absolute 0 of temperature only when it is in pure state. One thing is there. Second thing was that it is perfectly crystalline. What actually that does mean? And it is that disorder which gets introduced because of imperfect crystallization that leads to residual entropy. How? Let us see. Some substances are chemically pure but do not fulfill the requirement that the crystal be perfectly ordered. Pure hai, both the substance is pure, but it is for sure that it may be possible that the crystal is not perfectly ordered at absolute 0 of temperature. What it does mean? The crystal is not ordered? It does mean that, let us take example. In the crystals of carbon monoxide and nitric oxide, some molecules are oriented differently than others. What it does mean? Some molecules are oriented differently. If we want to observe this, let us consider a situation of if a crystal of carbon oxide is pure, chemically pure, and if it is perfectly crystalline, perfectly ordered, then in such a crystal what we understand is that all the oxygen atoms should point towards north direction and all the oxygen atoms should point towards, all the carbon atoms should point towards south direction. So, that there should be order of molecules, CO, 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 it is like that. All oxygen atoms to be inclined towards north direction and carbon atoms towards the south direction. But what happens in actual crystal is that all these molecules are not oriented in the same manner, that is oxygen pointing towards north direction and carbon pointing towards south direction, and therefore what it leads to is that in an actual crystal the two ends of the molecule are oriented randomly. It is as if two kinds of carbon monoxide were mixed. What it does mean? It means that all the carbon monoxide molecules are not oriented in a manner that oxygen is inclined towards north direction and carbon atom is inclined towards south direction. There can be reversal of orientation in space also of these carbon monoxide molecules. This occurs because of their almost same size of the two atoms which make up the molecule, and therefore it appears as if two kinds of carbon monoxide were mixed, one which is pointing upward, one which is pointing downward. So, if the two kind of such orientations are possible and suppose half molecules of carbon monoxide are pointing in one orientation and half molecules are pointing in other orientation, in other direction, then in that situation we can calculate the entropy of this mixing, of this mixed state of carbon monoxide, that is from the relationship we have just derived, that is delta S equal to minus NAK XA ln XA plus XB ln XB. If we say that both these kind of, there are equal number of constituent carbon monoxide molecules which are oriented differently in different directions, opposite directions, then XA, the amount fraction of one kind of directional molecule, become half, the other kind also become half. So, it means half ln half, half ln half. It becomes twice of half ln half. So, it becomes ln half. So, it becomes in total NAK ln 2, and Na into K is basically our gas constant, which is 8.314 joule per Kelvin per mole, and therefore R ln 2 actually is 0. ln 2 value is 0.693 R. So, therefore, the entropy of this mixed state of carbon monoxide should be, as per our formula, 5.76 joule per Kelvin per mole. But the observed entropy, this is called residual entropy of carbon monoxide, is 0.55 R, not 0.693 R, that is 4.6 joule per Kelvin per mole. What it does mean? It does mean that proportion of one kind of carbon monoxide molecules which have a particular orientation, their number is greater than that of the other number, and that is why one number become greater than half, and one amount fraction become greater than half, and one amount fraction become less than half, and that is how it leads to a little lesser value of this fraction, that is instead of 0.693 R it becomes 0.55 R, and that is how carbon monoxide molecule possesses this residual entropy of 4.6 joule per Kelvin per mole. So, what we have learnt basically is that because of the orientations of the crystallizing molecules in space, it appears as if two kinds of molecules which are having different orientations that are actually go to occupy the lattice sites and go to make up a mixed state at even at absolute 0 of temperature, which introduces randomness, and that is actually therefore the cause of residual entropy, which otherwise should not be, but it is because of this different orientations of these molecules in space and which lead to randomness. So, the ultimate reason is that the crystal is not perfectly ordered. There is disorder in the crystal even at absolute 0 of temperature. That is why we observe that there is a residual entropy. Having said this, now let us consider in the case of nitrogen oxide. Nitrogen oxide should also be 0.693 joule per Kelvin, 6.93 R, its residual entropy, if the number of atoms are in equal proportion. But what we observe, the number of atoms are not in equal proportion, one thing, from the observed results which suggest us that its residual entropy is 0.33 R, R means gas constant 8.314 joule per Kelvin per mole. It indicates different thing. In basically this observation is being explained with the help of the physical observation that has been made on the crystal pattern of nitrogen oxide. It has been observed that crystal of nitrogen oxide are dimers in nature, and if the nitrogen oxide NO do crystallize as a dimer, not as individual nitric oxide molecule NO. So, if suppose there are n number of molecules of NO, then there will be n by 2 number of molecules of the dimer, and in that situation if their orientations is to be considered of different kinds of NO, then that number would get half. So, it means 0.693 if we divide by 2, it almost leads to 0.33 R. So, it means this lesser value of, very less value of residual entropy compared to carbon monoxide of this nitric oxide can be explained on the basis of observation that nitric oxide exists as dimer. and that is the reason it almost leads to almost equal proportion of two different kind of orientations which are possible for nitric oxide. Those molecules have almost equal proportion, but because of the existence of nitric oxide in the form of a dimer, the residual entropy gets exactly half almost. So, that is 2.8 joule per Kelvin per mole. Having said this, another example is crystalline hydrogen. Now, question arises, in crystalline hydrogen there are again two atoms which go to make a molecule. In carbon monoxide there are two different kind of atoms, carbon and oxygen, which go to make up the molecule, and we talk about the orientations of oxygen atom pointing towards north and carbon atom pointing towards south and things like that we talk about. But what about hydrogen? Hydrogen molecule has two hydrogen atoms which are bonded through a covalent bond, single covalent bond. What is then? There should not be the cause of residual entropy. There is no evident cause, there is no randomness. It means there are no different orientations in space for the crystallization pattern of hydrogen molecule. Then question arises, then from where this residual entropy do exist? The experimental observations suggest that hydrogen also possesses residual entropy. So, what is the reason for that? That is a question of concern. In order to answer that, we can say that disorder is not the answer to explain the existence of hydrogen in the form of in some random state and to possess residual entropy. The answer lies in the distribution of the molecule over several quantum states. What is the quantum states basically? We must, in order to answer to this question, we must understand that ordinarily hydrogen is a mixture of ortho and para hydrogen. What is ortho and para hydrogen? There are two different kind of hydrogens which have different values of total nuclear spin angular momentum of charged particles which constitute the hydrogen atom. So, net result is that there is two different kind of hydrogen molecules, ortho and para hydrogen, which have different values of total nuclear spin angular momentum. As a result, rotational energy of ortho hydrogen is non-zero because it exists in 9 different quantum states, each have different value of nuclear spin angular momentum and corresponding to which there is different rotational energy, which is a finite value for ortho hydrogen, which exists in 9 different quantum states, and para hydrogen which exists only in one particular quantum state, has only a fixed, not different but fixed value of nuclear spin angular momentum. So, if you have pure crystalline para hydrogen at absolute 0 of temperature, it will have 0 entropy, but if you have ortho hydrogen or a mixture of ortho and para hydrogen, because of presence of ortho hydrogen in 9 different quantum states with different total nuclear spin angular momentum, their energies corresponding to different energies. Therefore, this leads to the fact that ortho hydrogen can be in any one of 9 different quantum states, and thus the system has a randomness and therefore a residual entropy. So, final answer is that if a system has to follow the third law of thermodynamics, 1, it should be pure, chemically pure. 2, it should be perfectly ordered, pure, perfectly crystalline. Let us add to this, there should be only a fixed, only one particular quantum state also, then only the entropy for such a substance would be 0 at absolute 0 of temperature. That is how the third law of thermodynamics puts the restriction on the nature of substance, because as you can see, the third law of thermodynamics apply only to pure perfectly crystalline substance crystallizing in only unique quantum state. Then the third law of thermodynamics will be applicable. That is what we make an observation. So, what we learnt from this whole discussion is what is the cause and reason for residual entropy, and all this discussion emerges from statistical interpretation of entropy. Now, having said this, we lead now towards the new concept called spontaneity and equilibrium. if you remember back, we had considered in the beginning also that criteria for a spontaneous change is, if you remember that through Clausius inequality we learnt that entropy change of a system should be greater than 0 for a spontaneous change and should be equal to 0 if it is a reversible process at an equilibrium state. So, and we further said that if we consider the system to be isolated and isolated in a way that there is system of interest and there is system of there is immediate surrounding, then the entropy change of the system of interest along with its immediate surrounding should be greater than 0, then the process will be spontaneous in such an isolated system. But now question arises that for an irreversible process, therefore, the total entropy goes on increasing and attains a maximum value when at the equilibrium is reached, delta has become 0. So, the two criteria we have: total entropy, total means entropy change of the system along with the entropy change of the surrounding should be greater than 0, means if in a particular transformation of the system entropy continues to increase, this means that there are some kind of real changes, spontaneous changes are occurring in the system. So, entropy change is an indicator towards whether we are having some natural change occurring or not, spontaneous change or not. Now, when entropy change, total entropy, that is change, that is system plus surrounding, becomes 0, it indicates that the system has attained a state of equilibrium. But the fact of matter is that the criteria of equilibrium requires not only the possible. Now, if we have to make use of this relationship of that total entropy change for an equilibrium is equal to 0 and is greater than 0 for a spontaneous process. So, if we need to develop this as criteria of spontaneity and equilibrium, then the problem with this criteria is that we need to talk not only of possible processes in the system, but also what kind of interactions the system has along with its surroundings. So, it means we need to keep monitoring the system as well as surrounding. So, therefore, this criteria, although is a very successful one in order to explain the natural changes. If you remember back, I said if there exists some indicator which changes in one direction if natural change occur and changes in another direction if unnatural change occur, then entropy, total entropy of the system plus surrounding is an answer to that question. We have developed a criteria, but this criteria has some lacuna. Lacuna is that we need to monitor the entropy change of the system along with the entropy change of the surrounding. So, it means we also need to consider all the time how the system interacts with the surrounding. But our effort should be to let the spontaneous process go on in the system and let us consider the state functions in the beginning and after the process completes, and then on the basis of which we should be able to make the calculations. So, this criteria, although is very important, is the first step towards setting up the criteria of spontaneity and equilibrium, but it is not sufficient. We need to therefore modify it itself in some other formula which incorporates only the which depends only on the state of the system, so that we just have a knowledge of state variables at the beginning and after the process is complete, and we can talk about the process whether being a spontaneous or not. Well, having said this, so it means now we need to move on with certain different criterias for what is the criteria of spontaneity and for the criteria of equilibrium of a physical process or a chemical reaction. Now, question arises how to develop such a criteria. For that, we say that now let us consider reversible transformation of a system. So, at any stage of the transformation of the system departs only infinitesimally. That was the characteristic of the reversible process, if you recall back. So, in a reversible system, it does mean that the system transforms yet remains effectively at equilibrium. So, the condition of reversibility we can say therefore is the condition of equilibrium. If it is so, then from defining equation of entropy, you recall back, the condition of reversibility is T ds equal to dq reversible. That was the combination of first and second law of thermodynamics, where we have coined the definition of entropy change. So, therefore, the condition of equilibrium is this equation 1, that is TdS equal to dq reversible. Having said this, now what is Clausius inequality? What it says for us? It says that for an irreversible change, TdS is greater than dq, whatever the heat involved. We would not write reversible here. Why? Because we are talking about irreversible changes. So, irreversible change occurs therefore in real transformation, and therefore is a natural direction of change which occurs spontaneously. So, therefore, what should be the criteria of spontaneity? This Clausius inequality which emerges from this, that is TdS should be greater than dq. So, equation 2 therefore becomes the criteria of irreversible change or spontaneous change, and equation 1 is the TdS equal to dq reversible is the criteria for an equilibrium condition. If we mix the two criteria, what we get? Combination of two criteria, we have TdS is greater than equal to dq. But in this equation, if equal to sign applies, then it means we are talking about dq reversible. If greater than sign applies, then we are talking about dq, not reversible but irreversible. Having said this, let us consider first law of thermodynamics. What was that? dq equal to du plus dw, that is equation 4. Using equation 4, if we make use of equation 4 in equation 3, that is instead of dq we write du plus dw, we get equation 5, TdS greater than equal to du plus dw. Now, having said this, for an isolated system, consider an isolated system. First criteria we are trying to develop. For an isolated system, du equal to 0. Because the system is isolated, it does not interact with its surrounding. Whatever the energy is present within the system will remain conserved. So, energy of the system will remain conserved means du equal to 0. Since there is no heat exchange with the surrounding, dq equal to 0. Since there is no work done by the system on the system, then dw also equal to 0. So, in that situation, what way the equation 5 transforms? Du equal to 0 and dw equal to 0, and therefore, in that situation, for an isolated system, TdS equal to greater than equal to 0. T we can take it to 0 side, 0 by T again 0. So, we have ds, that is entropy change under condition of constant internal energy and volume is greater than equal to 0. Why? Because when we say dw is 0, there is no exchange of work effect between the system and surrounding, it also includes work of expansion. So, expansion work requires volume change, and therefore, if dw is 0, then volume would also be constant, volume would also not be changed, du will be 0, then internal energy would remain conserved for an isolated system. So, du would be equal to 0, dw would be 0 and dv would also be equal to 0. So, therefore, for such a system ds uv is greater than equal to 0. It means this is we have developed a criteria for spontaneity and equilibrium in terms of state function. State function is entropy, which says the entropy of the system provided the internal energy as well as the volume of the system is kept constant should increase. It means the entropy for such a system should increase, in which the volume is kept constant, the internal energy is kept constant. Then it is an indicator that there is some spontaneous process going on in the system. And another criteria, and similarly we can develop another criteria, that is du, that is energy change under condition of constant entropy and volume is less than equal to 0. It means entropy of a system under condition of constant internal energy and volume tend to increase in a natural process, whereas internal energy of a system in a system where entropy and volume is kept constant tend to decrease in a naturally occurring or spontaneous process. So, these we developed two criteria of spontaneity and equilibrium, but in terms of state function, that is change in entropy and change in internal energy. But the problem is that isentropic and isoenergetic processes are seldom observed. So we need to talk about certain conditions in which temperature and pressure are constant rather than internal energy and volume or entropy and volume. So therefore, we will develop certain more important criteria of spontaneity and equilibrium that we'll do in our next session. So for the time being, I would say thank you very much for your viewing this program on chemical thermodynamics. Thank you.
On this note, I would like to thank sir for this lecture, and I hope friends that you have found this lecture to be extremely enriching and knowledgeable. And I would like to thank you people as well for watching this lecture. Stay tuned and keep watching. Thank you.